So yeah, I can start. So hello, I'm Kyung Do, fifth year PhD student in mechanical engineering, advised by Professor Monroe Kennedy. And today I want to share the two different ways to improve the robotic dexterity with optical tactile sensor, which is called as DenseTact. So we all imagine the robotic assistant, which is recently showed from the Tesla as helping us, such as folding t-shirt like this, which is, even though it's teleoperation, but to make this kind of assist robot happen around us, I think one of the key bottleneck is the dexterous manipulation. And researchers has been solved this issue using the external vision, as you can see in the left, which is the in-hand orientation task with just using a vision, or using a touch and vision at the same time. And it also showed that the touch feedback actually helps to do in-hand orientation or make much better than just using an external vision. But what if the object is too small to detect from the external vision, or the object is too hard to detect from the surface because of the occlusion, for example, whether the object is gathered in the same place and is in the cluttered environment. So I will share two different cases for solving this kind of issue. The first case is where we are thinking about the simple scenarios, such as grasping screws or small object from the cluttered environment, such as you can see in the right, and grasp and orient and classify those objects from the cluttered environment. So the external vision systems may be insufficient for detecting those objects because there's too many occlusions and there are too many objects, so we might need to train that model or scene a lot to deal with those issues by just using the external visual. And also grasping the small object by the previous gripper is not possible, so we might need to use a small size gripper or other kind of specialized gripper, and as well as the reorienting the small object might need regrasp motion or any other strategy by just instead of doing just simple grasping motion in here. So our study can efficiently solve this issue by using our optical tactile sensor, which is called as DenseTact. So there are a few ways to deal with this problem. For example, people are dealing with this problem by just grasping it and then reorienting unconsciously, and then do classification by either feeling the tactile feeling of the object or by just seeing the object. And I'm trying to mimic this kind of strategy in our paper, which can be pipelined as like this. First, we detect the object where the object is, and then grasp and do in-hand orientation to do better grasp or make stable grasp, and then classify it which of the object that we grasped. And for the first process, which is the detect motion, as you can see in the left, let's say the screws or any daily object are cluttered and it's really hard to detect from the external vision. And for here, to deal with the detect, we haven't used any other vision algorithm to use this. Instead of that, we use the depth information of the rear sense camera. So this is the scene that a robot will get. So we determine the highest point of the pile, as you can see in here, and then move the robot into the right direction to make the better or stable grasp out of this scene. And then we grasp the object out of the cluttered environment. So this happens with the gripper with the this 8 degree of freedom, which has four 2-axis dynamics and motors, and with the fingertips at using the optical tactile sensor as a fingertip. So this fingertip is called the DenseTact 2.0, which is one of the paper we made, published last year. So this is the sensor. So you can see it's really soft, and there is a camera inside of the sensor, so that the camera can determine the deformation of the sensor and estimate the net range as well as the shape of the deformed shape. So by I will skip this detail of the sensor, but the sensor estimates the shape and the force through this kind of unit shape or encoder-decoder shape network by a lot of training with the data set. So the input is the image, one single image, and it can determine the dense reconstruction of the shape as well as the net range of the sensor. And using this tactile sensor, we are able to achieve some kind of compliant gripper because the gel is too soft. So we can use it allows the gripper to adapt those uncertainties while we grasp from the cluttered environment. So while it can actually do some kind of distribute the force evenly while you're grasping some object or the small object, and it makes more stable or the more successful grasp by just using rather than just using rubber gripper or rubber fingertip, which is used a lot of robot tips or fingertips. So, and also since it's the tactile sensor, we can use those tactile feedback for as a control input of our next goal, which is the interfinger manipulation. And then, this is one of the range that the gripper can move. And by using those various movement of the various range of movement, we can achieve the in-hand interfinger orientation or in-hand orientation of the object while we grasp the object. So to do this, we define the state of the controller by depending or according to the feedback from the tactile sensor, which is the y coordinate position of the fingertip in the gripper frame, which is attached in the gripper, or the angle of the movement in this direction or this direction inside of course, in the gripper frame. And of course, the input is the 4 degree of freedom of the one finger of this gripper. And we can solve the simple Jacobian to deal with this controller, and then use the inverse Jacobian for deal with or to get the right input of the controller. And one of the important things to deal with this controller to deal with secure the stable grasp is the finding the right objective of the controller. And we define the objective of this controller by minimizing the data AB, where you can see in this right image, which is the minimizing the angle between the object and the middle line, which is the line between the center of this sensor and another center of one of the finger. And then by minimizing this data, so we can actually always make the small object is always in between the central line of those two fingers. And at the same time, while we also put the objective on the first state, which is the y coordinate of the fingertip, by maintain the grasp on object. So it's constant value, but depends on the tactile feedback of the sensor. So you can just keep maintaining the grasp on object while minimizing the data AB. And as I showed before, since it has the 4 degree of freedom like this, it has additional degree of freedom to deal with the stability inside of this Jacobian controller. And using this one, we are able to do the interfinger orientation. But we also tried many different strategies such as RL or optimization, using try to learn the dynamics of the sensor. But it actually didn't work well because first main issue was we used the Isaac Jim, but the Isaac Jim didn't have the right parallelized function or to deal with those multiple issues. Multiple programming at the same time with the deformable object. It does have the deformable simulation, but it's not allowed to do some kind of parallel computing. And also, even though it's possible, those self-deformable simulation is not quite accurate enough to deal with all of those like gel simulation, as you can see in here, which is really soft, and it always attached to the object while the gel has been deformed in like this way. So it's almost impossible to use, train the RL unless we use the real data set and do the motion all day long for our case, or we try to learn the dynamics by like collecting a data set of the grasping primitive like in this way, and then like collect the data set for the controller input with the while we grasp some of the object. But of course, this is also too noisy to use for the controller, and so we concluded that we only just simple Jacobian controller can deal with those interfinger manipulation more easily by just using a tactile feedback. And final step is the object classification. Since we are using this tactile feed sensor, which has the camera inside of the sensor, so we can estimate the depth out of this observed input. And then we filtered out using the DB scan to clusterize the deformed or the detected screw like this way. And finally, we can get 3 different images, as you can see here. The first one is the like the input from the camera of the DenseTact 2.0, and the second one is the estimated depth of the image, and the final one is the filtered or the clusterized information of the sensor. By doing so, you are able to like orient or reorient and crop using the PCA and like train the data set while collecting a data set from the like this process. The data set collection has been done with while we assuming those grasping happen with those 2 gripper or 2 fingertip. And we collected only 50 RGB and 50 corresponding depth images per each object type, while it has been fully observed or the partially observed at the And we also tried to collect the many different situations, such as 2 screws are like observed at the same time, even though it's not like handling all of the situation, like closing situation happens like that, but we try to collect all of the govern all of the situation happen during the classification. And since the data set is too small, which is 50 and 50 images per each label, and we try to pre-train the ResNet 18 for classify this label. And one of the key thing I think is that works well is we try to crop and reorient this like the image from the filtering or the estimation of the DenseTact. We try to like lift up some of the burden of the network by reorienting or cropping it by using the segmentation to like train the network as easy as possible. And by doing so, we were able to classify those like many different type of screws fairly well, as well as some of the daily objects you can see, which is still small to like deal with or do some convenient orientation with the existing RL or the other algorithm that has been proposed these days. So this is for pipeline, and finally we were able to achieve the more than 80% of the successful grasp, or like successfully classify the screw with the different heads or the different size of the length of the screws. So this is one of the demonstration results. So the first, the robot hand detects where the tile is, the highest tile point, and then move the like gripper slightly into the gripper point, and then grasp it like in this way. And regardless of whether it grasps 2 screws or not, we're going to classify it's been grasping 2 screws or the 1 screws at the same time, and then do some small in-hand orientation, and then classify it in this way. And we do this, we repeat this demonstration more than 200 steps, and like in this way, it's although like 10 times faster than before, and we are able to classify those objects easily from the cluster environment. So this is one of the solution I proposed for the dealing with the small object. But what if the gripper or the fingertip is needed for grasping tiny object from the flat surface, table or the desk, which is easily can be seen in our daily life. So to deal with those problems, we are doing proposing many. As a human, we are proposing many different strategies. Like for example, for the coin, we are using the fingernail, and or for the really small objects such as the hex nut or the basil seed, we are trying to attach the object to our fingertip, like by just tapping it and then try to stick the object to our finger and then grasp it. And I think those strategy is really useful for and try to adapt those strategy into our fingertip. But turns out there are tons of problems for the existing robotic hands or the robotic grippers with the existing fingertip. So, like for example, some robotic hands are too large to grasp such small objects, or we need some kind of specialized two-finger gripper to give it those flat surface grasping, or most grippers are lack of the capability to detect the tactile feedback out of those gripper input, or while we grasping something from the flat surface. So to deal with those issues, we also designed another tactile sensor, which is called the DenseTact-Mini. So you can see it's successfully grasping a clip on the right side, which can deal with grasping the multi-scale object from the flat surface. So the objective of this study is trying to grasp and sensing the various size of the small object, including the 1 millimeter size of the basil seeds to thin objects such as coins or the clips, and general object at the same time from the flat surface. So to deal with those problems, we designed a new sensor or the new fingertip by making it much smaller, as you can see in here. Which has the similar design scheme but has the fingernail in it. So the price is less, it's much cheaper than the previous one, and using the smaller size of the camera module as well as the faster FPS. But the main difference from the previous sensor is the applying the attachable or detachable fingernail design. So we can keep it's been fixed with the screws, as you can see in here, and then we can change those fingertip material by the other one. And turns out that the most matter from the fingernail is the friction coefficient between the surface and the fingernail itself. So we can choose various materials of the 3D printer to make this fingernail. And then, of course, there's a LED inside of the sensor, and we're dispersing the LED lights to make the make everything as small as possible. And we propose 3 different strategies for using this DenseTact-Mini. First one is tap grasping, fingernail grasping, and then the fingertip grasping. First, the tap grasping is the grasping the object with using the surface interaction forces, such as the electrostatic force or the van der Waals force. So it depends on the surface material, or the depends on the shape of the object or the weight of the object, as well as the contact area between the gel and the object. So since the gel is clear enough to make some kind of van der Waals force as well as the electrostatic force, so you can see the PEX nut, which is M2 scale, M2 size, can be easily picked up with just by tapping motion, which is sticking to the finger, as I first proposed it in the human strategy. So by doing this, we can achieve the tap grasping strategy with this fingertip. And the fingernail grasping, which is using the fingernail to deal with like grasping the thin object out of a flat surface. So there are two different strategies working on like grasping by using the fingernail. The first one is the rolling contact. So while the fingernail cannot slide beneath to the bottom edge of the object, this kind of strategy happens. So this rolling contact has been happens as you can see here. So it's making rolling contact while grasping a coin, like in this way. I will show you again. Or the other way, which is much simpler than that, is while the radius of the tip of the fingernail is smaller than the radius of the object, you can go directly beneath to the object in this way. So by using two different strategies, we can achieve like high grasping success rate with the fingernail, while grasping like dime or really small size of the object, even in the flat surface like this way, achieving more than 90% of the success rate. And the final strategy is using the fingertip, which is the normal grasping with using the two fingertips. So we like evaluate our sensor, we make the detection pipeline by using the tactile sensor input or the camera input inside of the sensor. Like we can achieve like determine whether it's pressed or like it has been getting the object correctly by like pressing it again or checking or even detecting a scraping motion when we try to scrape it out like in this way. So like we finally evaluate our sensor with using multiple objects like such as bases or the M1.6 nut or M2 nuts or paper clip like battery or the really small size of such as that dime and as well as the bearing. So I think the main takeaway from like this presentation is that soft tactile sensor can grasp, classify, and do reorientation tests from the cluttered environment rather than just using some like complicated algorithm by just achieving upgraded on the hardware, as well as we can also like grasp really thin or small object by using the surface interaction force or the fingernail design on the optical tactile sensor. Thank you.
One thing I'm really curious about, because you mentioned picking up tiny objects from a flat surface or like from a cluttered surface, but it's more like laying down like this way for the screws. But if you're like picking up, for example, a paper clip along its like direction where it's very thin, like it's like almost stepping out of the surface, will your camera be able to like actually catch what exactly the shape is, because you need to find the center of mass to like minimize.
Exactly. So that's the reason I like assume the cluttered environment, and that's like one of the limitations it's not some kind of generalized like environment, but it's always assuming the cluttered environment. We get since so that there is those clutter of a pile of the object can easily move or like working as a liquid so that they can easily change while we grasp like and just keep changing the environment at the same time. So that's the one of the way to solve those issues with the soft tactile sensor. And I think most people are focusing on not changing the environment, but making really like preserving the environment as much as possible, and then try to grasp it by like finding the right grasp primitive before we grasp something. But instead of that, we don't have to worry about those kind of like complicated algorithm or process, but just grasp it because it's cluttered environment.
Is time history of the image useful?
Yeah, I will say the time history of the image is really useful for both sensor. Like for the DenseTact-Mini, we can see like how the impact happens while we try to grasp something like at that moment. So we can use that impact if we have enough the frame length, then we can use that impact or the history for achieving the other kind of the algorithm or like contact information or like extract.
How would you expect to use the history information? How would you incorporate it?
That's really great question. So I'm thinking about using those information to deal with estimating the force of the sensor itself, like estimate the detected force by like since it's just the impact, so impact can be achieved from it's really some kind of enemy of the controller, like for I think so. I think we can achieve those vibration state can be handled with this kind of like.
Yeah, I was thinking of something simpler, which is that like when you grasp something, I mean you have not just the current frame, but you have previous frames.
Oh, right, yeah.
And it's the same object.
Yeah, right.
But the condition of also, which means you have more information.
Yeah,
also it's viscoelastic. Yeah.
Yeah, I think that's a really great idea because since we still need to keep make a contact while we're doing some kind of those like complicated motions. So those historical input is really important for dealing with those our algorithm or the others.
Other questions? Okay, go ahead. Yeah,
I
please.
guess just out of curiosity, so you're just using one single camera for detecting the object, right?
Yeah, one single.
In that case, is there a way for you to like estimate the distance between your operator and the object?
So right now, you mean the first paper?
I mean, just like this is on the desktop, but like how far are you going down?
Oh yeah,
just
we are
keep
using
going until you're like getting a sensor feedback.
Yeah, so we are using the desk camera of the rear
okay.
sense, so yeah, we can use it.
You mentioned that you can also orient the tiny object. How do you do that?
So those orientation can be done with the simple Jacobian controller, as I mentioned before. So in here, so like we are trying to, since our gripper has 4 degrees of freedom and which is 4 level, it has the 4 level joint, we can like move the gripper like in this way or in this way or in this way. So by like setting up the state of the controller with the Y and this motion or this motion of the state, and selecting the object as minimizing the data AB from the tactile feedback, we can do the stable grasp or the reorientation test.